Alright, it's Mrs. Butcher here, and this video is about graphing general rational functions. So our last video that we did was on doing graphing simple rational functions. We're going to take this to more complex polynomial fractions now. And to graph any of these, we have 6 rules that we need to memorize. These rules apply to vertical asymptotes, the horizontal asymptote, x-intercepts and the y-intercept, and then a slant asymptote, which we may have sometimes, and holes, which we may have sometimes. So 5 and 6 are the hardest part. But these are the 6 things you always want to look at. So let's just start with the first one. Alright, vertical asymptotes occur because you cannot divide by 0. And we saw this in our simple rational functions. All you have to do, no matter what your rational function looks like, is set the denominator of the fraction equal to 0 and solve for x, because that will give you the x values that you can't use, and so those will be the equations of your vertical asymptotes. And I have an S on asymptote because you can have more than one. Alright, the second thing is your horizontal asymptote, and there's no S on this. There can only be one horizontal asymptote, if there will be one at all. And for that, we have 3 separate situations. If the numerator and the denominator are the same degree, and we did this yesterday with the linear over a linear. If they have the same degree, they're both quadratic or they're both cubic or whatever, then you're going to take the ratio of the leading coefficients. So if I had 2x to the 5th power plus 9 over 3x to the 5th power minus 2. These are both 5th power, so you just take this ratio, 2 over 3, and your horizontal asymptote would be y. Y equals 2 over 3. It's always y equals. Alright, so that's if the numerator and the denominator are the same degree. Now, we could have the numerator being a larger degree, or we could have the denominator being a larger degree, and we have 2 special ways to remember that. So the first one I want you to talk about is what happens if it's big on the bottom, because we've done that before. 1 over x, that's a constant on top and an x, a linear on bottom. Alright, so if your numerator is smaller than your denominator, if it's big on bottom, that's what we did when we did the first one. It's like 1 over x. That's bigger on the bottom. It's got a higher degree on the bottom. I want you to think of a famous celebrity who is just a little bit big on bottom. Alright, see, this is J-Lo. And J-Lo is big on bottom. And so if your fraction is big on bottom, then J-Lo rhymes with 0. And I want you to think, big on bottom, J-Lo 0, y equals 0 is where your horizontal asymptote goes, every time. Okay, and then the third situation you could have is if your numerator has a higher degree or a higher power than your denominator, so if it's bigger on top. So I want you to think of a celebrity who's big on top, and you have to think back to Miss Butcher's childhood here. Think of about a old country singer who is famous for being big on top. Okay, see, this is Dolly Parton. You've seen her in some movies. She's big on top. I mean, look how big that hair is. My goodness. But you can't see it in this picture. I'm just going to have to tell you, and you'll have to take my word for it, that Dolly Parton has no asymptote. I'm sorry about the handwriting. I can't find my stylus, so I'm writing with my finger. But anyway, yeah, so if it's bigger on top, think Dolly Parton and think none. No asymptote at all. No horizontal asymptote, I should say. Okay. Alright, the third thing is the x-intercepts, and yes, you can have more than one. So if you recall, when you draw a graph, and then it crosses the x-axis, whatever that looks like, that's where y equals 0. So if you took your fraction and set it equal to 0, the only way that it would equal 0 is if the numerator was 0. 0 divided by anything is 0. Remember, the bottom can't be 0. We've already talked about that. So all you have to do is take the numerator and set it equal to 0, and then you'll know your x-intercepts. Yeah, I'll type that. Looks better. Set numerator equal to 0 and solve for x, and those are your x-intercepts. Alright, there's only going to be one y-intercept, and so once again, if you think of the graph, the y-intercept is where x equals 0. So to find the y-intercept, you just plug a 0 in everywhere you see an x and solve for y. Plug a 0 in everywhere you see x, solve for y. That'll tell you your y-intercept. Alright, the fifth thing is the slant asymptote. That happens only when The degree of the numerator is 1 power higher than the degree of the denominator. And the way to find your slant asymptote is kind of tricky, but that's why we spent a day doing our long division. You are going to just take the fraction and you're going to do polynomial long division, and because the degree of the numerator will be 1 more than the degree of the denominator, you'll always end up with a linear solution, and that linear solution will be your asymptote. If you end up with a remainder, you just ignore the remainder. All you have to do is get the linear part of it. You can stop. You don't have to find the remainder, and we'll practice that in a little bit. Alright, and then the 6th rule is about the holes. A hole is an infinite point in the graph where if you were to factor the top and the bottom and have a factor cancel out, you might have a hole. And I know y'all hate factoring, but you really need to remember how. It's still very important. So we're going to factor, and then if any of your factors cross out, you're going to graph your function all based on the simplified version, except you're going to take the part that you crossed out and you're going to set it equal to 0 to figure out the x value of your hole. And then you'll take that x value and you'll plug it in to your simplified fraction to get the y value of your hole. And once again, we will practice that in a little bit. Alright, and then the rest of the graph, you can just make a table. You will have your calculator, so you'll be able to get a good idea of what the rest of that graph is going to look like, and then you can just look at the table in the calculator and plot points off of that. Alright, so we're going to do a few examples. Hang on just a second. This example is y equals 3 over x squared plus 2. So we're going to think about the 6 things we need to definitely have. The first thing being our vertical asymptote. Remember, to find the vertical asymptote, you set the denominator equal to 0. So if I said x squared plus 2 equals 0, and I subtracted 2 from each side, and then I tried to take the square root of negative 2, that doesn't exist. So that means we don't have any vertical asymptotes. If you can't solve for x when you set the bottom equal to 0, you don't have any vertical asymptotes. Alright, second rule, horizontal asymptote. For the horizontal asymptote, you look and see if this is J-Lo or Dolly Parton. And in this case, it's a squared on bottom, so it's big on bottom, think J-Lo. And when you think J-Lo, think y equals 0. So our horizontal asymptote goes right here through y equals 0, which is along the x-axis. Alright, the third thing we want to think about, x-intercepts. So if I were to set this thing equal to 0, if I wanted to try to set the numerator equal to 0, I wouldn't get anything. Because if you say 3 equals 0, that doesn't tell you anything about x. So for our x-intercepts, if I were to ask you what they are, you would just say none. It doesn't cross the x-axis. You have an asymptote there, so it kind of gives you a hint that you're not actually going to cross it. Fourth thing, the y-intercepts. So we're going to plug in a 0 for x, and if I took 3 over 0 squared plus 2, then I'd have 3 over 2. That means that the y-intercept is at 0, 3 halves. 3 halves is 1.5, so it's going to be right there. Alright, the fifth thing we want to think about, slant asymptote. That only happens if the top is 1 degree higher than the bottom. We don't have that situation. So slant asymptote, if you don't have one, write the word none. And the last thing is holes. We didn't have to factor this, we didn't have to factor this, and nothing crossed out, so are there any holes? No, no holes, none. Alright, so we've done the 6 important parts. Now all we have to do is make a table. We can look at the calculator to get the numbers. You can look at the graph and see what it's supposed to look like. Alright, if you look at the table, you get a point at 1, 1. We have a point at 2 and 1/2. And then we have a 3 and 0.3 approximately. And we know that that's approaching the asymptote, so it's not going to go any lower than 0. And then you can also look at the negatives. Because it's x squared, if I plug in a negative 1, I get the same thing as if I plugged in a positive 1. If I plug in a negative 2, it's the same thing as when I plugged in positive 2. and same thing with the 3 and with all the values. So this is going to be symmetric across the x-axis, the y-axis. We're going to have a point at 1, 1, and at negative 1, 1, at 2, 1/2, and at negative 2, 1/2, 3 and 0.3, negative 3, 0.3. So it makes this, looks like a little mountain or a little anthill. It's kind of a strange graph, but some of these are going to graph kind of strange, and that's okay. So now tell me about the domain of this graph. The domain is, remember, it's left to right, and it's going infinitely to the left and infinitely to the right with no breaks in between. So we could just say all real numbers, or negative infinity to infinity. The range is the y values. The lowest y value we have this asymptote at y equals 0. It's kind of like a force field that graph can't pass. So the lowest y can be is 0, and it won't be able to touch it either. So soft bracket on the 0. And then the highest y value is going to be the top of the hill right here, which we know is at 1.5, 3 halves, or 1.5. And it does touch that, so we put a hard bracket on that one. All right, new example, y equals x squared minus 9 over x squared minus 4. And the first thing you always want to do is see if you can factor anything, and in this case we can't. The top is the difference of squares, x plus 3x minus 3. And the bottom is the difference of squares, x plus 2x minus 2. And then you see if any of those factors will cancel out, but in this case none of them will. So then the first thing we want to look at is the vertical asymptote. Remember, to find your vertical asymptote, you set your denominator equal to 0. So if I set x plus 2 equal to 0, I would get negative 2. X equals negative 2. If I set x minus 2 equal to 0, I would get x equals positive 2. So this one is going to have 2 vertical asymptotes, one at negative 2 and one at positive 2. And that's all right. You can have lots of vertical asymptotes. Just depends on the power of the problem here. All right, so then the second thing is horizontal asymptote. We look at this and we say, is it J-Lo or Dolly Parton? And it's actually got the same power on the top and the bottom. So when you have that, you take the ratio of the leading coefficients. This one is a 1 and this one is a 1, and 1 over 1 is 1. So our horizontal asymptote is at y equals 1. And we'll put that on the graph. All right, Xintercepts. Set the numerator equal to 0. You're going to have 2 Xintercepts. You're going to have one at negative 3, 0. And one at positive 3, 0. So we can put those on there. There's a point there, and there's a point there. Y-intercept, remember you plug a 0 in for x, so we have 0 squared minus 9 over 0 squared minus 4, which is going to end up being 9/4. So 0, 9/4, which is 2 1/4. So 2 1/4 is about right there. We need to talk about the slant asymptote, but that only happens when the top is 1 degree higher than the bottom, so in this case we don't have any. And then you need to think about the holes, but we didn't cross out any factors, nothing canceled, so there were no holes either. The rest of the graph, you can just make a table. You can use your calculator and look in there and get some points. You know that you're going to have 3 main regions of this graph. You're going to have a region over here, and a region in here, and a region over here. So make sure you pick x values all the way across to plug in. Alright, so looking at this table, we already know that negative 3, 1 right here is a point. So let's plug in a negative 4. You can look in the calculator, and when x is negative 4, y is about 0.6. So it's going up a little bit. And then when x is negative 5, y is about 0.8. So we know it's going to approach this asymptote and not cross it. And then on this side, it's just going to come down and approach this asymptote and not cross it. All right, in the middle here, we could plug in a negative 1. If you look on the calculator on the table, negative 1 is 2.67, so 2 2/3. So that's 2.7 is about right here. And then if you plugged in a positive 1, it would be the same thing. And that's a little bit above this right here, this y-intercept. So what that tells you is you've got this U shape. And of course, if you look at the calculator, you can see it, the U shape in the middle. And then on the right, because it's x squared for both of them, we know it's going to be symmetric. So we can just say plus or minus 4.6 and plus or minus 5.8. And it mirrors what the other side is doing. Now our domain for all of this, this one's tricky. We start at negative infinity because we've got an arrow on the end. But then you have a break at your asymptote. So you put comma and then your asymptote's at -2, but it doesn't actually touch it. Then it picks back up again right after -2. And then you have this U shape, and then it hits the other break at +2. Then you pick back up after the break, 2, and then that one's going out to infinity. So you have 3 parts of your domain just like you have 3 parts of your graph. Your range on this one, you only have one asymptote, so your range is -infinity, and then it stops at the asymptote at y equals 1. It doesn't touch it. And then, and I am running out of room, sorry, it picks back up right here. And it actually does touch that value, and remember that value was 9/4. So we're going to go with 9/4 and then to infinity. And it does actually touch that point, so I put a hard bracket on there. All right, example 3 says y equals x squared minus 2x minus 3 all over x plus 2. And you want to factor the top if you can here. X squared minus 2x minus 3 would give you x minus 3 and x plus 1. And that's all over x plus 2. So nothing cancels out. This is our function. You can put it in your calculator to graph it. First thing we want to locate our vertical asymptotes by setting the denominator equal to 0. So that means x equals -2. If x was -2, we would be dividing by 0. Only one vertical asymptote for this graph. Write your horizontal asymptote. This one is big on top. Remember, big on top is Dolly Parton, and she has no asymptote. So no horizontal asymptote here. All right, x-intercept. Set the numerator equal to 0. And if we do that, we're going to get 3, and we're also going to get -1. So we have 2 x-intercepts. At -1, 0, and +3, 0. Okay. Y-intercept, plug in a 0 for x. That would give us 0 squared minus 2 times 0 minus 3 over 0 plus 2. So -3/2, -1.5 right there. Slant, that happens when your top is 1 degree higher than the bottom. Well, that means that we need to do some long division. All right, and I didn't leave room for that, so we're going to do it on the next page. But before I do that, let's finish this up. Holes. We didn't cancel anything out, so none. All right, now I'm going to turn the page so that we can do our long division to find our slant asymptote. Remember, we're going to take this original problem and we're just going to set it up like we did the other day. So we're going to say x plus 2 on the outside into x squared minus 2x minus 3. Now you look at the x and you say x times what is x squared, and that is x. So you multiply. X times x is x squared. X times 2 is plus 2x. Then you subtract. So that's 0. And then -2 minus 2 is actually -4x. We'll bring down the minus 3. X goes into -4x, -4 times. Now, the trick is we would now have to multiply -4 times x, -4 times 2, subtract, and then whatever's left is going to be your remainder. But I don't know if you remember, but I told you the remainder doesn't matter. All that matters is what you get up here. So the equation for our slant asymptote is y equals x minus 4. So I'm going to try to get that last page back up, and then we'll plot that on the graph. Okay, so our slant asymptote we determined was at y equals x minus 4. That's just a line with a y-intercept of negative 4 and a slope of positive 1. So I'm going to dash in my my diagonal slant asymptote. And then the rest of the points we can get by looking at the calculator. Now be careful because if you just graph it on a 10 by 10 window, you're only going to see, sorry about that, this top branch of the hyperbola. But you do have a bottom branch too. You'll have to change your window a little bit and look, or just look at the table. But we have points, -3, -12, down here, and -4, -10.5 here, -3, -12 there. So we know it's going, -7, -12. So there, not there. So it mirrors the other side like that. Now the domain and the range of this is kind of tough, so I'm not going to make you do it, but domain would be -infinity to -2, -2 to infinity. Range would be -infinity to the top of this hump, and then the bottom of this part to infinity. Alright, this is the last example. We've got y equals 2x cubed plus x squared all over 2x plus 1. And once again, the very first thing you always want to do is factor, just to make sure things will or won't cancel out. So here on the top, I can factor out a greatest common factor of x squared, and then I have 2x plus 1 left. And on the bottom, we have 2x plus 1, which doesn't factor. But these two groups match, so you can cross them out. And that means that all we really have is y equals x squared. And that's a very easy graph to do. It's a parabola. However, because we crossed out a factor, it's going to be a parabola that has a hole in it. So everything that we do for this graph is going to be based on only y equals x squared, except the hole. Vertical asymptote, parabolas don't have asymptotes, none. Horizontal asymptote, none. Xintercept. If I set x squared equal to 0, x equals 0, so 0, 0. Yintercept. If I plug in a 0 for x, y is 0, which makes sense because 0, 0 is an x and y intercept at the same time. A slant asymptote, we don't have any. We don't even have a denominator after we cross everything out that cancels, so no slant asymptote. So that leaves us with the holes. Or in this case, hole. There's only one. To find the hole, you take what you crossed out, 2x plus 1, and set it equal to 0. So that means we have 2x equals -1, x equals -1/2. That is the x-coordinate of your hole. But a hole is a point, and you need a y-coordinate. So to find the y-coordinate, you take this x value and plug it in to the remaining equation. So if I said y equals -1/2 squared, I'd get +1/4. So your hole is at -1/2, +1/4. It's a point. And you're going to mark that on the graph with an open circle. So at -1/2, well here, let me draw some axes. And at -1/2, 1/4, I'm just going to be a little bitty right here. I'm going to draw an open circle. And then we know our x and y intercepts is 0, 0. And we know this is y equals x squared. It's a parabola, 1, 1, 2, 4, 3, 9, and so on. So all the rest of it just gets sketched like a normal y equals x squared. The only difference is it has that open circle on there because it has a hole. So remember, to find the hole, you first take what you've crossed out, set it equal to 0, get x. Plug that x in to the remaining equation and get y, and that's the ordered pair of your hole. Okay, for this graph we need a domain and range. So the domain is all real numbers except for the whole. So all real numbers except negative 1/2. So I'm going to say negative infinity to negative 1/2, and then negative 1/2 to infinity. So when you're doing domain and range, you write it just like you would with an asymptote. So our range, this one starts at 0, hard bracket because it touches 0, stops at the whole, which is at y is 1/4, picks up again after the whole, 1/4, and then goes on infinitely to infinity. And that is the lesson for today. I know it was long, and I'm sorry, but this is one of our harder lessons. So you guys have a good night, and I'll see you tomorrow.